My name is Svetlana Kohn. I am a professor of the Department of Nanotechnology and Metallurgy, Karaganda Technical University. The name of our discipline is crystallography. What is it? Crystallography is the science of crystals. It is clear. Since 18th century, all the bodies with a natural rectangular shape have been called crystals. You can see here. All metals and metal alloys have a crystalline structure. That is why it is necessary to know the crystallography laws for further successful study of metallography. Taking into account the contemporary views of the crystal definition, the subject and the problem of crystallography can be raised as follows. A crystal is called a solid body in which all the elementary particles, atoms, ions, molecules are arranged in strict regularities at large distances. The subject of crystallography is analyzing these regularities, giving their description in a qualitative and a quantitative manner, and on the basis of these descriptions developing and predicting the crystal properties. A crystal is characterized by three main properties. The first, homogeneity. Homogeneity is the property of the body to be the same in its entirety. However, this is true only the ideal crystals. Real crystals are characterized by imperfect, so the notion of homogeneity for real crystals is relative. The second, anisotropy. What is it? Anisotropy is unlikeness of properties to the parallel directions. And the third property of crystal is ability to self-cut. It is a property of the body to take under certain conditions multifaceted form. This property is unique only to the crystal. Crystallography is characterized by the double approach to the description of crystalline matter. They are both treated as a discrete as a sorted medium. Discreteness means that the crystal properties cannot be identical where a particle is and where is not, or in the places where there are particles of different kinds. However, to describe many properties of the crystal, it is sufficient to consider the amount that is greater than the particle volume, but smaller than the volume of the crystal itself. In this sense, crystals are considered as a continuous and homogeneous medium. These words is a little introduction to our topic. And now we begin with the topic number one. The name of this topic, the concept of a translation and the space lattice. What is it? We consider an ideal crystal. Its structure has not imperfections. All identical particles are arranged in parallel infinite series. The distance between particles in the majority of crystalline materials are 10 nanometer. About 1 billion particles are distributed in the length of 1 millimeter in the crystal, which can be regarded as an infinite series. The shortest possible distance between identical points in a series is called a translation unit or a period of identity. If you shift the point for an infinite series for a period of identity, a series aligns with itself. It is a symmetrical translation by which the point is repeated in space. This transformation is called translation. Repeating any point using translation, we obtain an infinite periodic series of identical points on the distance a, 2a, 3a, and etc. You can see here. The same points interconnected with translation are called nodes of the series. A side does not necessarily coincide with the material points. If you repeat the same point with the help of another translation, what is not parallel to the first one, you will obtain a flat grid. You can see here. This grid is fully determined by the two translations, A and B. Parallelograms with vertical sides, other sides are called mesh grid. Here, we choose a unit cell in a flat grid. Repeating it with the help of translation, we obtain a flat grid filling the entire plane without gaps. A unit cell is chosen so that it meets the following conditions. It will reflect the symmetry of the grid best. B. It will have the right angles if possible. C. It will have the smallest area. A primitive unit cell, for example this, is a cell inside which there are no sides. Each side located at the top of this cell belongs to both of the other four. Here, thus the cell accounts for only 1/4 of this side. The cell which accounts for one side can be chosen differently, but the area of these cells will be identical because the area that accounts for one side is constant for a given grid. The number of sides per unit of area is called the vertical density of the grid. On this slide, you can see the main terms of this topic: elementary translation, and you can see the new term, uncompleted translation. Please remember these terms. Primitive cell and reticular density. Now we can introduce with the new term space crystal lattice. What is it? Now we'll consider three arbitrary point non-compliant translations which do not lie in one plane and repeat it endlessly in space. We obtain a special lattice ABC. These translations are incomplete. They don't lie in the one plane, and if you repeat with unit cell, we obtain the space crystal lattice. What is it? Space crystal lattice is a three-dimensional system of sides. The three translations, a translation group can be chosen differently, but the principles are the same as in selection translations of the planning grid. Parallelepiped constructed on three elementary translations A, B, C is called a unit cell. As in the planar grid, the volume of the primitive unit cell doesn't depend on its shape and is a constant value for the lattice. It is equal to the volume per one side. Thus, a special grid can be specified in three ways: as a free basic non-compliant translation, the second way as a system of equivalent units transformed into each other with the help of three translations, And the third way as a system of identical parallelopipeds densely filling the space and coinciding with one another in free translations. The edges of a unit cell, the other words, an elementary translation, are the directions in the space lattice in which the period of translations is the lowest and the best reflects the crystal symmetry. Translations are desirable to be mutually perpendicular to each other and to have equal time duration. Of course, this is not always possible. Selecting the main translation is important because they determine the crystallographic system of coordinates. Destinations of crystallograph axes coincide with the edges of the unit cell, and large-scale pieces of the axis coincide with the edges length. Thus, a space lattice is an infinite three-dimensional periodic formation with the help of which the same points are revealed in the crystalline space. You can see what is it, the crystalline lattice, and of course it is necessary to remain with term. It should be clearly understood that a unit of a special lattice does not necessarily coincide with the material point. You can see the special law. We will study this term later on the practical lesson. And at the end of our topic, I want to introduce you the main laws of crystallography. The first law, the law of Stenen, or Stenen's law. What is it? When a crystal grows, here, the particles are arranged in a regular and symmetric series grids lattices. It means that the crystal grows in such a way that its faces grow parallel to themselves. Please, here, you can see here. The area of faces, therefore, can vary for various reasons, but the mutual inclination of the crystal faces remains unchanged. This is a quantitative law of crystallography opened by Nicholas Stenen in 1669, and now this law is known as a law of Constancy of Angles. In all crystals of the substances under identical conditions, the angles between the crystal faces are constant. What is it, identical conditions? Identical conditions mean that the temperature and the pressure, that is, if the substances have several polymorphs, as ferro, for example, we talk about only about one modification. This law implies that the angles between the crystal faces of one substance, despite their outward differences, shape, size, and even the number of faces, is always constant. The law of constancy of angles makes it possible to reduce all the variety of forms of crystals to a set of angles between faces and to represent them with the help of projections. This law has played a prominent role in the development of crystallography. Before the discovery of X-ray diffraction, all crystals of a matter were characterized and distinguished from each other only by the angles between the faces. At that time, the main method of diagnosis was to measure the angles with a gonio special equipment. The special equipment is a goniometer. And now I want to introduce you the second main law of crystallography, the Wolfberg condition. You can see this, the analytic equation of this condition, whereas the D and in the planar distance, n is integer, and lambda is a wave's length, and theta an angle of reflection. What is about the Wolfberg condition? The diffracted rays are mutually reinforcing if the path difference between them is a whole number of wavelengths, as like n is equal 1, 2, 3, and etc. This equation expresses by Wolfberg's condition, and this law was opened independently by Bragg and Wolf in 1913. In other words, if the beam with the wavelength lambda is incident on the set of atomic planes parallel to each other and separated by the distance d, it generates a diffracted beam at the angle theta. Thus, flat lattice in the crystal structure under certain angles of incidence can reflect X-rays. These reflections, more precisely the maxima of the intensity of the diffracted rays, are recorded. The diffraction patterns display the uniformity of crystal symmetry and give an opportunity to measure the interplanar distance d, the angles between faces, etc., and consequently to diagnose the crystalline material. At present, X-ray analysis based on the Wolfberg's law is the fundamental method for studying crystalline phases. Now I want to finish our lecture. I think it's necessary to repeat this presentation yourself. You can do it because this presentation is open in NetBrace. Goodbye.